hash of A equal to n, this means whenever I write hash of A is equal to n, that means A contains n elements. Okay, so I'm moving to the next theorem. This is an important one and the results are very much familiar to you, but we have to prove it here. This is 1.3.4. The theorem says that if A contains n elements, A is a finite set with n elements, and B contains m elements, A intersection B is equal to 5 means A and B are two disjoint finite set. A contains n elements and B contains m elements. Then the set A union B contains n plus m elements. That is, we have to this is the first statement you have to prove. So A is a finite set with n elements, B is a finite set with m elements, and they are disjoint sets. So their union will contain n plus m elements. Okay, so let's prove this first. Then I will go to the next part of this theorem. To prove this, what all things we are given? We are given that set A contains n elements. When will you say that a set contains n elements? When there is a bijection from 1 to 3 etc. up to n to A. So this means there exists a bijection. I will call it as F from 1 to etc. n to A. Now what all things are given? B contains m elements. So number of elements in B is equal to m. This means there exists a bijection. I will call it G from G is from where to where? G is from 1 to etc. m to B. Okay, and we know that A intersection B is empty. There is no common elements for A and B. All the elements are distinct. So, if there is a bijection F from 1 to 3 etc. up to n to A, then this is a bijection. Bijection means it is onto. So I can write A as, this A is what I can say, this is on our function F is onto. If the function F is onto, then a range of n5, no, not n5, it is nn. Range of nn is A itself. Range of nn, this is the set nn. Range of nn is A itself. So A can be written as f of nn. That means this A can be written as f of 1, f of 2, etc. f of n. Similarly, we have a bijection G from 1, 2, 3, etc. up to m to B. So I can write B as G of n m, so that I can express B as G of 1, G of 2, etc. G of n. Okay. Now, what is A union B? Okay, we have to prove that A union B contains m plus n elements. So we have to define a bijection from set 1, 2, 3, etc. n plus m. and A union B. So let's draw a figure. Here I have 1, 2, 3, etc. n, then n plus 1, n plus 2, etc. Here I have n plus m, and I am writing A union B here. F of 1, f of 2, f of 3, etc. f of n, then A is over, I am starting B. It is g of 1, g of 2, etc. g of m. So this is our n plus m, and this is A union B. We have to define a bijection between them. So I am mapping 1 to f of 1, 2 to f of 2, 3 to f of 3, etc. n to f of n. Okay. Now I am mapping n plus 1 to g1. n plus 1 is mapped to g1. n plus 2 is mapped to g2, etc. n plus m is mapped to gm. So from the figure itself, it is clear that this is a bijection. Now how can we define this function? I will call this function as h. So h is a function from 1, 2, 3, etc. n plus m to A union B, such that h of k, if k is equal to 1, 2, etc. up to n, what is h of k? h of 1 is f of 1, h of 2 is f of 2, h of 3 is f of 3, etc. h of n is f of n. So h of k is f of k. Now if k is equal to n plus 1, etc. n plus m, then what is h of k? n plus 1 has the image g of 1. n plus 2 has the image g of 2. How do you get 1 from n plus 1? Subtract n. How do you get 2 from n plus 2? Subtract n. Okay. So this is nothing but g of k minus n. So if we define h like this, h is a bijection from n plus m to A union B, so that A union B contains n plus m elements. Okay, this is the first part of our theorem, and the second part says that suppose A is a finite set with m elements. So A is a finite set with m elements, and C is a subset of A, and C contains only one element. So number of elements in C is equal to 1. What we have to prove is the set A minus C contains m minus 1 elements. So our set A contains m elements, and C is a subset of A which contains only one element. So A minus C means we are removing some element from A, a single element from A. So what remains is m minus 1 element. The result looks trivial. But how to prove this? The hint is that we can use the first part of the theorem. If you prove something, you can use it to prove the next result. How can we prove? So in the first theorem, what we are talking is, we have two finite sets. Okay, we have two finite sets. Both of them should be disjoint. Both of them are disjoint, and we are talking about their union. Okay. Here, whether I have two disjoint finite sets, I have an A minus C here, and I have C here. What about A minus C intersection C? This is empty. So, A minus C and C are disjoint. Clear? Then, by the previous result, we can say that number of elements in A minus C union C is equal to number of elements in the first set plus number of elements in the second set. What is A minus C union C? So this is A, this is C. A minus C is this set. Union C. So you will get the entire A. So A minus C union C is nothing but A. So number of elements in A is equal to number of elements in A minus C plus number of elements in C. We are given that number of elements in A is M, and we don't know what is number of elements in A minus C, and it is given that number of elements in C is equal to 1. So M is equal to number of elements in A minus C plus 1. Then what is number of elements in A minus C? It is nothing but M minus 1. Okay, I hope you understood the result. We have taken two disjoint sets, and then by the previous result, number of elements in the union equal to sum of number of elements in each set. We use that and we will get number of elements in A minus C is equal to M minus 1. Now, the third part of the theorem says that if C is an infinite set, C is an infinite set, and B is a finite subset of, or B is a finite set. The result says that C minus B is infinite. So, we are given that C is infinite, B is finite. To prove that C minus B is infinite. So, here also we are using first part of the theorem. So, we need two disjoint sets. Whether we have two disjoint sets here? Yes, and they are C minus B and B. They are disjoint. So their intersection is equal to 5. Suppose C minus B is finite. What we have to prove is C minus B is infinite. And I am assuming that C minus B is finite. Means C minus B contains some n elements. So number of elements in C minus B is equal to n. We are taking so. Similarly, we are given that B is a finite set. So, number of elements in B, there is some number of elements. B has some certain number of elements. I am calling it as M. So, B has M elements. C minus B has n elements, and both of them are disjoint. Therefore, by first part of the theorem, number of elements in B union C minus B is equal to number of elements in B plus number of elements in C minus B. This means, what is B union C minus B? B union C minus B is C. B is a subset of C. So I have told that, but I haven't written here. So number of elements in C is equal to number of elements in B plus number of elements in C minus B. So C contains m plus n elements, but we have given that C is an infinite set. If C contains m plus n elements, it is a finite set. So this is a contradiction, since C is an infinite set. So why we arrived at such a contradiction? Because we have assumed that C minus B is finite. So our assumption is wrong. That means C minus B is infinite. I hope you understood the theorem. Go through the proof several times so that you will be more clear about the proof. Okay, so study well. All the best.